So I think this will be the final topic of this semester, and this lecture is on the notion of invariance. Um, I am just to be clear, a really big believer in invariance. I think it's one of the most foundational ideas in all of mathematics. I think it's one of the most powerful ideas. Um, so I really want to spend some time us trying to understand this. I do want to put some questions about invariance on your final. So take your time trying to absorb this, and then trying some problems, and let's spend the last week of class and some time, office hours during finals week, to sort of get together and discuss this stuff, okay? So we've already seen one invariant in group theory, and that's the invariant of being cyclic. And I just want to get into more of this, sort of abstract this a little bit, and look at some other invariants and how they might be useful. So uh, let's talk about this. So in the last few handouts, we've seen how useful the following fact is in making arguments. If G is a cyclic group and L is a group that you know to be isomorphic to G, then L also has to be cyclic. I think we proved that rigorously on the last handout. And so such a property is called an invariant. And again, I think they're really important. So let's talk about what an invariant really is. Now, just to be careful here, as a heads up, invariant can be used both as a noun and as an adjective, okay? And I'll use it both ways. So let P be some property that groups can have. The whole point is that a property is something that a group either has or it doesn't. It's a yes or no question. And being cyclic is a property. You're either cyclic or you're not. It's a property. Being abelian is a property. You are either abelian or you're not. Okay, so let P be a property. Not all properties are invariants. Some are. Okay, we say that P is an invariant if whenever G has property P, and you know that G is isomorphic to L, then L also has to have property P. That's what makes a property an invariant, when it satisfies this rule here. When G has it and L is isomorphic to G, then L also has it. All right? And as we proved before, the property of being cyclic is an invariant. There are lots of other invariants, but let's talk about why you care. That might not be obvious. Here's a standard problem in group theory. Here's a standard issue problem when you have questions of classifying certain kinds of groups. Suppose you had two groups, G and L, and you want to know if they're isomorphic or not. This is a standard question you would ask in any classification problem, right? Given G and L, are they different or are they the same? Are they isomorphic or not? And this can be hard to parse out in general. Now, there are two potential answers to the question. Yes, they are isomorphic, or no, they're not. And how you argue your answer depends on if your answer is yes or no. In some sense, the yes answer is easier because there's less to do. If you think the answer is yes, that G and L are isomorphic, then you got to prove they're isomorphic somehow. And this is most often done by actually sitting down and constructing an explicit isomorphism alpha that runs from G to L. You just sit down and you have to find the function from G to L. You got to check that your function is one-to-one. You got to check that it's onto, and you got to check that it's a homomorphism. Okay? That's if the answer is yes. There's only one thing to do. Find me an alpha that works. Okay? However, if you think the answer is no, this is existentially a lot harder. You must prove that no such alpha exists. Now, there are probably lots and lots and lots and lots and lots of functions that run from G to L, and you would have to prove that none of them work. None of them are isomorphisms. There could be infinitely many functions that run from G to L. You would have to check that none of them work. That is a lot to ask. So you somehow must prove that no bijection can also be a homomorphism. That's one way to do it. Or you could vice versa this. You could prove that no homomorphism can ever be a bijection, right? Either way, that could be a lot of work. There could be, unfortunately, infinitely many things to check. So when you think that your two groups are not isomorphic, that can be very hard to prove unless you knew how to use invariants. Okay, a better way to handle the no case is to use an invariant. Here's what I mean. Suppose that G and L are groups, all right? And suppose there's an invariant P, and G has that invariant, but L does not have that invariant property. Then there's no way G and L can be isomorphic. They must not be isomorphic. Okay? So this is sometimes a very easy way to prove that two things cannot be isomorphic. You go out and you find some invariant property that G has and L does not, or vice versa. Maybe L has it, but G does not. Then they can't be isomorphic, and the proof is easy. Suppose you were wrong and they were isomorphic. Well, since G has an invariant property and is isomorphic to L, then L has to have the invariant property. But we said it didn't have the property, contradiction. So you're done. It's very easy. But there is a talent to finding the right invariant property to use to make your argument work, and that will depend on your groups G and L. Okay? But this is a really clever strategy, and this is why invariants are so important. Let me give you just one example. I'm going to leave it to you to think about other examples, and that's part of the practice problems that I'm going to include at the end of this handout for the exam. Okay? But let's just do a basic example first. Example 1. I claim the group Z mod 16 and Z4 cross Z4 are not isomorphic. They are both order 16. Okay? So what you do is you take an element A comma B from Z4 cross Z4, and you notice that 4 always kills it. So 4 times AB is 4A, 4B. But of course 4 is 0 and 4 is 0, so 4 times A is 0 and 4 times B is 0, so you get 0, 0. So 4 wipes out any element. So every element of Z4 cross Z4 has to have order 4 or less. Of course it must be 1, 2, or 4 by Lagrange. It can't be 3. So what this proves is that Z4 cross Z4 cannot be cyclic because no element can ever have order 16. The best you can do is 4, right? So Z4 cross Z4 is not cyclic, all right? But being cyclic is an invariant. And Z4 cross Z4 does not have it, but Z16 does. Z16 is cyclic. And therefore, Z16 and Z4 cross Z4 cannot be isomorphic. Okay? So let's take a break and we'll come back and we'll look at what else you can do with invariants.